Well, Jeremy, I am calling your bluff. I'd sort of joked about solving these puzzles with the GA, and that is exactly what I've gone and done. So, we've got two puzzles so far. I've managed to solve these with a mere 515 lines of code. If I expand that out, you'll see, there you go, 515 lines. And that's on top of the GA as well. So it has actually taken me several hours to program all of this. And it would have been far, far quicker to solve them by hand. But never mind. Just quick, brief overview of what the code comprises. We've got our class for our pieces, which for some reason are called vehicles, even though it includes swimmers and buoys. But we've got this just stores the location of the piece, the length of the piece, and whether or not it's rotated. We've got actually a fairly complex puzzle kernel down here at the bottom, and this injects a little bit of intelligence into the mix. So if you wanted to solve this with the GA, you could just set up a very simple kernel where the GA just directly tells it where to put pieces, and the kernel puts those pieces down, and then checks whether or not the constraints of the puzzle have been reached. So for example, this buoy has to be here, and this one has to be here, and then we've got to have the end of a piece here, and so on. The problem with doing that is that the GA has to then learn what the constraints are, and it does do this, and GAs do learn, and the way they do that is through a process of trial and error, and then by encoding the knowledge of what was successful into the genetics of the population they're working on. But there are so many constraints in this problem that isn't really feasible to do in a sensible amount of time. But we can inject a bit of intelligence into the puzzle kernel itself and make it put down the first few pieces to meet these constraints, like this one here. So, and then all we need to do is specify, or have the GA specify, which piece it's going to use to satisfy that constraint. So that's basically how it works. And if we quickly look at how the puzzles are actually encoded, we've got just the size of the board. This is puzzle 1 we're looking at here on the left, which is 10 by 10. And then for each one of these pieces that are already placed down, then we just have a requirement here saying what location it is and what type of piece it is. And you can see that this type is an end, and we've got the middle here, which is in location 2,5, which corresponds to that. And then the number of blocks we have in each row and column is just stored in these two lists here. So in total, that means that we have, for puzzle 1, 20 design variables, a 20-dimensional problem, discrete maths problem as well, which makes things a bit more interesting. You would think that you might need 3 design variables for every piece, apart from the buoy, which would need 2. But because we've already got a few pieces placed down, that brings the number down from 30 down to 20. So here we have the GA solving puzzle 1. This is just a little animation of it moving the pieces around. What we've actually got plotted is we've got the best 10 individuals from every generation. If we move on to puzzle 2 now, puzzle 2's actually turned out to be harder to solve than puzzle 1, and that at first seemed a bit surprising because only 18 design variables are required for puzzle 2, and the main reason for that is that we have 3 end constraints already on the board, whilst with puzzle 1 we had 2 end constraints on the board plus a middle constraint, and that middle constraint requires 3 design variables to specify how to solve it, whilst the end constraints only require 1. So straight away that cuts down from 20 to 18 design variables. So we've lopped off 2 dimensions there. You would think that would make it easier, but the GA did in fact struggle more to solve this problem. Nevertheless, it did manage to solve the problem, as you can see.